Hello everyone, I am Ghanshyam and welcome all of you to the electric neuron. Today we are going to see the source transformations in network theory which are very important to your examination like GATE, RRB, SSC and ESC and your university exam also. It is very important to attend all these questions. Okay. So in the previous lectures we have already completed the star delta and delta to star conversion of the resistive element. In this video we are going to see the star to delta and delta to star conversion of the capacitive network. Then we will see about the source transformation. Okay, so why we need source transformations and what are the purposes to implement source transformation in the network theory, we are going to see here. Okay, so before starting our video lectures I want to tell you that if you like the video, please share to your friend and also subscribe to this channel so that you will be benefited and your friend also be benefited to this lecture. Okay, so let's start. So see, this is the conversion of star to delta and delta to star network of the capacitive element. Okay, so first we need to see the delta to star conversion. So this is the delta connection, CA, CB and CC capacitance are connected in the delta manner. So we need to convert the C1, C2, C3 capacitance value in form of the star connection. Okay, so it is the opposite to that resistance case or inductance case. Okay, so first here for this we know the formula, that is Z is equal to XC, that is capacitive reactance, is equal to 1 by 2 pi Fc. Okay, so here Z is inversely proportional to capacitance value, so that's why 1 by C1, for C1 this impedance we need to write 1 by C1. Okay, because only the capacitance value is there. Okay, so that's why we need to write the 1 by C1 value for this capacitive network. Okay, so for 1 by C1 what is the formula? Same formula put here, 1 by CA into 1 by CB divided by total capacitance, that is 1 by CA plus 1 by CB plus 1 by CC. Okay, so this is the value of star connected C1 value. Okay, so like that the star connected C2 value, that is the nearby capacitance value, that is CB, 1 by CB into 1 by CC divided by total capacitance 1 by CB plus 1 by CC plus 1 by CA. Okay, so this is the value of 1 by C2 or impedance across this. Okay, like that if you want to find the C3 value, 1 by C3 or impedance across this, then that is equal to nearby capacitance 1 by CA into 1 by CB divided by total capacitance 1 by CA plus 1 by CB plus 1 by CC. Okay, so this is the solution of that delta to star conversion. Like that if you want to find the star to delta conversion, that means this is the star network C1, C2, C3, this is our star network, so we need to convert the delta network, that means we need to find the CA, CB, CC. Okay, so for this impedance 1 by CA is equal to multiplication of all the capacitance value divided by opposite arm capacitance. Okay, so see here, so for this impedance 1 by CA is equal to multiply this into this 1 by C1, sorry this is not like that, for CA multiply all this capacitance, that means 1 by C1 into 1 by C2 plus 1 by C2 into 1 by C3 plus 1 by C3 into 1 by C1. Okay, so this is the numerator side. Like that for denominator what we have to do? The opposite arm impedance, that is what is the opposite arm impedance across this? This is the C2, so here 1 by C2. Okay, so like that you have to find the 1 by CB and also 1 by CC. Okay, so this is the star to delta conversion of the capacitive element, and this is the delta to star conversion of the capacitive element. Now we need to see one problem on star to delta conversion. So see, this is the one network. Here it is asking about to find the equivalent resistance with respect to A and B. This is the network where A point and B point. Here the resistance 1 ohm and another resistance 1 ohm, and between 3 ohm, 6 ohm and 1 ohm, 1 ohm resistance is connected. So here this is the star network, this is also star network. So what we have to do first? So we have already discussed the star to delta conversion. Okay, so put here in this figure. In this figure only we need to put the star to delta conversion. Then only we can able to find the easiest solutions. So whatever the easiest solutions that can be easily found by transforming this network to delta network. Okay, so this is the step 1. See, first we need to convert this star network to delta network. So here what we have to do? Convert this network. So this is the resistance connected between this point and this point. This is RC resistance, and this point to this point RA resistance, and this point to this point RB resistance. Okay, so all the resistance here. So first we need to find the RA resistance. For RA resistance, multiply the all the resistance connected across the star element and added them. That means 1 ohm into 1 ohm plus that 1 ohm into that 1 ohm plus this 1 ohm into this 1 ohm divided by opposite arm resistance. That is, what is the opposite arm resistance across the RA? That is this. Okay, so this is your solution. So 1 into 1 that is 1, 1 into 1 that is also 1, 1 into 1 that is also 1, 1 plus 1 plus 1 that is 3 divided by 1 is equal to 3. Okay, like that you have to find the value of RB and RC. So after calculating the value of RB and RC, this is the step 2. See, this 3 ohm this and this 6 ohm are connected across this 3 ohm and this 3 ohm. So they are in parallel manner. So what we need here? So this 3 ohm and 3 ohm get parallel connection. So 3 divided by 2 is the equivalent resistance. So what is the 3 divided by 2? 1.5. The value that is 1.5 here we have find. Okay, like that here also 6 ohm and 3 ohm are in parallel connection. So 6 into 3 divided by 6 plus 3 that is 2. Okay, so after finding this we need to place all the value of the resistance whatever you have find here. So after seeing this element, this is the resistance, 2 resistance are connected in parallel a series manner. So added them. So after adding we find that the equivalent resistance that is 3.5. Okay, so this 3.5 resistance and 3 ohm resistance are connected in series manner, a parallel manner. So here what we need here, take parallel connection of this 3.5 and 3 ohm. So 3.5 into 3 divided by 3.5 plus 3 that is 6.5. So this is the equivalent resistance in between the point A and B. So this is our solution. So now come to the two important points that are very related to or very important to your MCQ type question. Okay, so see the first point, when resistance of equal value or equal value, when resistance of equal value transform from star to delta resistance increase by their time. That means if there is a star connection, then if you want to find or transform this star network to delta network, it have the same resistance value. That means if 1 1 1, then the delta value will be increased 3 times. That means 3 into 1, 3 into 1 here also 3 into 1. So it is 3 times the star network. Okay, And this is another term or another important point where if capacitance of equal value transform from star to delta capacitance it is decreases by 3 times. That means if there is a one capacitance and another one capacitance here, all those capacitance are same value, then the capacitance value is, now let me erase first. Okay, so now see, this capacitance value will be decreases from star to delta conversion. Okay, that means 1 divided by 3 here, 1 divided by 3 here, here also 1 divided by 3. Okay, so please remember these 2 points, those are very important. Now come to the source transformation. So why we need source transformation? Source transformation because of the complexity of the network. So we need to transform this complex network to a simple network by the source transformation only, and then we need to find whatever he is asking. Okay, so see here, this is the voltage sources and resistance are connected in series and that are short circuited so that current will flow. So what we need to do here, we need to transform these sources. That means if there is a voltage sources, then we need to transform this voltage sources into current sources, and if there is any resistance connected to this voltage sources in series manner, then we need to convert current sources with the parallel connection. Or if there is one current sources, then we need to convert this current sources to voltage sources. Or if it is Norton theorem, then we need to transform this Norton theorem to Thevenin theorem. Okay, so here the voltage sources, so voltage sources value will be transferred to the current sources, and resistance series connection will be transferred to the parallel connection, and the current sources will be transferred to the voltage sources. So the current sources value is 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 equal to Is short circuit current, that is equal to voltage sources divided by resistance. Like that, voltage sources be open circuited voltage, that is equal to Is into Rs, multiplication of both current sources and resistance. So it is the Norton theorem and it is the Thevenin theorem. So there, those both the network are opposite, but the actual solution is same. Okay, so here is one question. So it is asking about to find the current flow in the ideal diode of the circuit shown. So we need to find the current across here in this diode. Okay, this is the ideal diode. Okay, so here the 10 volt sources with the 4 ohm resistance are connected in parallel manner. Here also 2 ohm resistance and 2 ampere impedance and 1 ohm resistance are connected in series manner. So here we need to transform these sources, and here also we need to transform these sources for our easy solution. Okay, so transform this voltage sources to current sources. That means I is equal to voltage sources 10 volt divided by resistance 4. So here I is equal to 10 divided by 4, that is equal to 2.5 ampere. Okay, and then put it here 2.5 ampere with the parallel ohm resistance 4 ohm. Okay, and another 4 ohm is here, and here also there is 2 ampere and 1 ohm. So we need to transform this current sources to voltage sources. That means voltage sources is equal to current into resistance, that is 2 into I according to the Ohm's law. So multiply them, then we will got what? Voltage sources, that is equal to 2 volt. So 2 volt into series resistance, that is 1 ohm across here. Okay, so now what we do here, this 4 ohm and 4 ohm are in the parallel connection. That's why we are taking here parallel connection, then we will get the equivalent resistance is equal to 2 ohm. So after we got the 2 ohm and the 2.5 ampere, we need to convert this 2 ohm and 2.5 ampere current to source transformation from current sources to voltage sources, and the parallel resistance to the series resistance. Okay, so for that voltage is equal to I into R. So I is 2.5 and R is 2 ohm. So multiply them, then we will get 5 ohm. Okay, so this is the 5 ohm resistance, and here polarity is the same. That means the current will flow like that sign. So R polarity also from this to this, that means minus to plus. Okay, and this 2 ohm will be there, 2 ohm. Okay, so now put here KVL equation. See, this is the 5 volt and this is the 2 volt. So here this is the positive potential and this is the negative potential. Okay, so this voltage is greater than this voltage, so that's why our diode is in forward mode. So diode can conduct electricity now. Okay, so now put the KVL equation, or you also apply the formula I is equal to V by R. So here this is the 5 voltage and this is the minus 2 volt, because of the polarity are in opposite direction, divided by total resistance, that is 2 ohm plus 1 ohm, that is 3. 5 minus 2 is 3, divided by 3, so 3 by 3 is equal to what? 1 ohm, 1 ampere. I is equal to 1 ampere. Okay, now it is clear to you. If it is not clear to you, then ask me in the comment sections, I will clarify your doubt. Okay, now comes to the dependent sources. See, we have already know the independent sources. What are the independent sources in the previous 2 to 3 lecture. Okay, see, this is the linear dependent sources. If the some value is there with the current sign, that means it is the which sources? It is the sorry, it is not like that. If the plus and minus sign is there, then it is voltage sources, or if arrow sign is there, then it is current sources. Okay, so if something value with the current sign is there, okay, if something value with the current sign is there, then it is current control. Okay, like that here also voltage control. So this is the figure of current control voltage sources, and this is the figure of voltage control voltage sources, and this is the figure of current control current sources. This is the current sources with the control by current. This is the voltage control current source. Okay, so here B is equal to IR and A is known. Okay, and it is the B, there is no unit of V, and C, there is also no unit, and here D is in mho, that is I is equal to B divided by R, or the unit of D is mho. So this is the non-linear dependent source. So that means if there is a square or q term, then it is a non-linear dependent sources. Okay, now see one question related to this. Find the current in the 2 ohm resistance. This is the 2 ohm resistance, so we need to find across this current. Okay, so what we need to do first, this is the one current sources with the 1 ohm resistance, and this is another voltage current control voltage sources is there. Okay, sorry, it is voltage control current sources is there. So we need to transform this from this current sources to voltage sources with the voltage sources with series resistance. Okay, so here we have transformed this network to voltage, that means V is equal to I into R. So I is 1 ampere and R is 1 ohm. So 1 ampere into 1 ohm is 1 volt. Okay, so this is 1 volt with the series resistance. Like that here the current sources should not be changed. Okay, so here note that one point, while applying the sources transform from the dependent sources, wherever dependent sources magnitude depend without disturbing that element transformation can be applied. So the value that cannot be changed, the magnitude that cannot be changed. Okay, and the direction also be not changed. Okay, so after finding this, we need to apply the KVL equation here, then we will get the value I value. Okay, so this is the 10 volt and this 1 ohm 1 ohm resistance here and another 1 ohm resistance here and another 2 ohm resistance here. So add them because of they are in the series connection. So 2 plus 1 that is 5 ohm with the current I. So 5 into I. Okay. So here another 1 volt is there. So minus of 1 put here, and this is the Vx divided by 2. So here Vx divided by 2, that is equal to 0. Then Vx is equal to what? Vx is equal to I into 1 ohm. So put here I into 1, that is I divided by 2, that is equal to 0. Okay. So after transforming this from Vx network to I sources, then we will get I is equal to 2 ampere. So this is our solution. Okay. So this is complete. See you in the next lecture. Thank you.